right. Well, good morning. Good morning, friends. Hope we're doing okay. So today we have another coding slash virtual lecture. And what we covered last time was, in essence, unconstrained optimizations. So this is an optimal controls course, so there is an optimization component to it. We covered some controls. Now we're covering the optimization for the optimization part of controls. And what we specifically covered were optimizations without constraints. What do I mean by that? So the idea was that let's go back to our little whiteboard here. Little whiteboard. Let's see. Today. Okay. What we previously covered were these unconstrained optimizations. And you might be a little confused. You might be like, hey, I remember last lecture so vividly. We had things like constraints, okay? Well, you're correct. Keep in mind that we had this example problem, which was our fencing problem, okay? And the idea, as you've known many, many times, is that we're going to have some width and some height. Although this time I'm going to be smart. I'm going to call it a length and a height to avoid using the W in multiple instances. We have some length and height of some fence. You want to maximize the area. But you had some limit. We had some limit to the amount of fencing that we could use, and that was a perimeter of less than or equal to 40, right? Now, that's sort of the bare minimum of constraints, kind of. I mean, Jack had pointed out previously that we can't have negative length and negative height, and that is very, very important, as we talked about. Sometimes optimizations can be too clever for their own good, and they can come up with solutions that are just not possible, but technically solve the problem, right? But you can have perimeter as less than or equal to 40, or you could say that perimeter was equal to 40, right? And we solved this problem in a variety of ways. One, we tried to solve it by hand. One, we solved it in MATLAB using gradient descent. We also solved it using something a MATLAB function called fmin_con, which is their. So we'll write some of this stuff out. So the way we solved this previously by saying 2L plus 2H must be equal to 40. So this was, say, what we called an equality constraint, right? It's an equality constraint because it must be equal to 40, right? Now, it's a little bit, let's just say, constraining, because theoretically for this problem, no one's telling you necessarily have to use all 40 meters of fencing. But we kind of intuitively know, because we're smart people, that if you want the most area, you got to use as much fence as you can, right? So we could say, hey, let's make these equal to 40 as an equality constraint. So if this is an equality constraint, that means I have a relation relating my two decision variables, which relates length and width to each other, right? At which point I can solve, I can solve this constraint so you have length in terms of height or whichever, right? And then you could substitute it back in and basically use this constraint to make one in terms of the other. Question. Yeah. Thank you. I'm sorry. I got a little ahead of myself. Thank you. Applause. That is supposed to be length and height. Got it? Yeah, length and height. Old habits. Okay. So you could say, hey, well, then 2h is equal to 40 minus 2l, basic algebra. You're all very smart people to say that height is equal to 20 minus l. And as a result, our cost function, which we said is not area, but negative area, because we want to minimize negative area, which then maximizes area, okay? This means that it's equal to minus 20 minus L, times L. That's right. Now we have a cost function which only has one variable in it, okay? So what we did is we used the constraint, the equality constraint, to solve for some variables and then optimize the remaining decision variables. Right? That's what we did. And so what we could do is that we said, hey, we have some cost function here. We would then solve for the first order necessary conditions, which are taking the gradient, which, by the way, you could always list with that symbol right there. Okay, the upside down triangle is your gradient, your capital Del. Okay, and you have to set that equal to 0. That's your first order necessary condition. That's your first order necessary condition, right? And that's how we solved it last lecture. Okay, it's one of the ways we solved it by hand. However, this trick of solving for equality constraints and turning it into an unconstrained problem, see, we turned the constrained problem with more variables into an unconstrained problem with fewer variables. That's what we did. And if you can do that, that's really nice. Because then not only are there fewer variables to work with, so you have fewer derivatives to take for your gradient, you also only have to solve this first order necessary condition to figure out if you're at a critical point. And then you can check if you're at a minimum by checking the Hessian if you would like. Okay? But you don't always want to do this approach. Okay? Where we turn it into an unconstrained problem. Okay? Unconstrained. You don't always want to turn it into an unconstrained problem. Sometimes you want to actually be able to work with the constraints as you have them. Well, why might that be? Why might that be? Well, for one, this problem here, it was super easy to solve for one variable in terms of the other, right? Super easy algebra. You do it in your sleep. In fact, you might because it's early in the morning. But many equations get very difficult, get much harder to solve. Even with computer solvers, sometimes they are impossible to solve. Okay? So you can't always do this. And even if you can, sometimes the expressions, the algebraic expressions you're looking at become super complicated. Okay? When you're solving these things out. So then it'll make your derivatives super complicated. It's not always a good idea. Okay? That's number one. Number two, I gave you an example with an equality constraint, right? With an equality constraint. That's something I can solve for. I can say that, hey, this variable must be equal to this expression. But if it's an inequality constraint, there's an entire space. There's an entire space of places that that variable can be, entire range, right? So you can't just solve for it and then substitute and get an answer. It doesn't work like that. At least it's not easy. Not easy. So what we need are approaches to solve constrained optimization problems. Okay? And as we get started here, I do want to give you a little bit of background here. We haven't really talked much about how you actually write out these optimization problems mathematically. Like, how do you write them out? So here is the general form of an optimization problem. And just a tease for next lecture, which hopefully will be in person. Hopefully be in person. We have another name for optimization problems. Okay? And we're going to talk about this more next lecture. And it's called a program. A program. So just a tease for next lecture, we'll be talking about programs. And when we say program, we literally just mean optimization problems. Okay? And what does it look like mathematically? Okay? Well, the idea is that you have some set of decision variables W, lowercase w, and W star, okay, is going to be our minimum. It's going to be the solution to our optimization problem, is equal to, and I'm intentionally putting a little space here. I'm leaving it blank on purpose, because I'm going to fill it in. It's equal to the minimum of f of w. What is f of w, friends? You can feel free to pop in my ears or into the chat. What's f of w? Cost function. Oh, in unison, no less. It's the cost function. Thank you. That's our cost function. And then we will say subject to all the constraints that we have. Okay? So we actually say, just down below, we say ST, that means subject to, okay? And we could say G EQ, sub EQ for equality constraints, of W must be equal to 0. Those are your equality constraints. Again, they must be equal to 0. And if we have any inequality constraints of W, they must be what, friends? They must be less than or equal to 0. Great. This is what it looks like to write an optimization problem in math. Almost, because we have this little blank here. Okay, this little blank here. What does that blank mean? Well, I'll motivate this. As this is currently written, we all know what a minimum is, right? We all know what a minimum. And so let's say we have an example where we have a W and an f of W, and this is our function, right? We have eyes that can see that the minimum is right there at the bottom of that curve, right? If you can, in case you can't see it, it's at the bottom of that curve. It's like at the bottom of a parabola. So what is the minimum? We would say the minimum is this value right here. That's the minimum, right? Let me zoom in so you can see a little better. That's the minimum. Pointing at, make that a little clearer. Pointing at the minimum. However, when we're doing an optimization problem, when we're running an optimization problem, we don't necessarily want to know just what the minimum value of f is. What we really want to know is the value of w that gives you that. What choice should we make that gives us the best solution? That's typically what we want, right? So we'll call that w star, which is equal to, we don't say the minimum. What we want is the input argument to the function, the w, that gives us the minimum. So we call that the arg, A-R-G, min. Okay? We want the input argument that gives us the minimum. So that's arg min, arg min. We filled in that little blank space, and we put a little w in there saying, hey, what do we want? We want the w that gives us the minimum. That's what an optimization problem looks like in general. Any optimization problem you can put in this form, okay? We specifically will be talking about in this course almost always where w are real numbers, okay? So we'll almost always say for this class, w is an element of all real numbers n. So that means that, oh, it's a vector. It's a vector with n real numbers in it, as we talked about, okay? In this class, but you could totally have other types of programs that have different kinds of variables. But for our purposes, we'll talk about those, okay? So this is an optimization problem or a program that has constraints, right? It's a constrained optimization problem, okay? So how do we solve a problem that has constraints? Well, I'm glad you asked. So let's scroll down here. So let's approach solving a constrained optimization problem or a program in general. Okay? And let's start with only equality constraints. Equality constraints is going to be a little easier to explain and a little bit easier to wrap our head around. But there's a pretty easy extension to inequality constraints, which I think is so cool. Okay? So in general. So let's consider only equality constraints. So we're going to say w star is equal to the arg min of where you're going to return w of f of w subject to the constraint, and we only have equality constraints. So we'll say g of w is equal to 0. Okay. There is this are only equality constraints. That will be our problem. Okay? In general. But to come up with a way to solve this in general, let's think about a very specific example. Let's go back to our fencing problem. Let's go to let's write that in terms of a program. Our w star, this is fencing. W star is equal to arg min. And I'll get to the MATLAB shortly. MATLAB is coming. Is equal to minus length times height, where you want to know w, subject to the constraint that 2L plus 2H minus 40 equals 0. Hopefully that's fairly obvious how you get that from our previous perimeter constraint. This is our fencing problem. Okay. And what I'm going to do is I'm going, yeah, question, go ahead. Question for the chat. The question is, can we just assume that everything here after the argmin is assumed to be part of it? Yes. Yes. Totally reasonable assumption to make. Absolutely. I'm trying to remember an example where that has not been the case in my career. So I think you're safe, at least for the purposes of this class. So cool. Good question. Fantastic question, Jack. All right. So we can assume everything here is in the cost function. That's our cost function. Now, my friends, let's open up MATLAB. And what we're going to do is we're actually going to plot our cost function. This will be hopefully fun, okay? So I'm going to plot my cost function. I'm going to go to MATLAB right now. Hopefully you all can see our good friend MATLAB. I've just opened up a brand new folder, a brand new MATLAB window. And what I want to be able to do is plot our cost function here without constraints. All right. So what I'm going to do is say that, hey, I'm going to plot a range of L. And we'll have it go from 0 up to 40. Okay. So if I were to say from 0, and we'll do linspace. We'll go from 0 to 40. And we'll do 100 points in the linspace. And I'll hit semicolon so it doesn't print out 100 points. Okay? And my height, h, I'm going to do the same thing. Linspace, 0, 40, 100 points. Okay? So I have my L and my h. Okay? A bunch of points. Now, if I'm going to want to plot my cost function across those two variables, right? So I have two decision variables. Let me go back to here. My decision variables are W is L and H. W is L and H. And I'm going to want to plot both of those. It'll look something like this, where I have L, I have H, and there's going to be some 3D plot here, right? See that? Kind of vague 3D plot, where up here is our cost function, which is a function of W, which is L and H. A little bigger so you can see it. That's all that is, just little 3D axes. We need a surface, right? Okay, so if you want to plot this surface in MATLAB, what we're going to want to say is, hey, we want our cost function f. Oh, we haven't plotted it yet. So we want that cost function f to have the cost of every combination of L and H. And apologies for jumping back and forth. That means if we want to make a grid of a bunch of L's and H points, and then to find out what the cost function is on all of those. Okay? So what we're going to do, is say mesh grid. What we're going to do is we're going to create a mesh grid. What is mesh grid? For those who don't remember or haven't seen it before, what it does is it lets you take in two vectors, or even more potentially, of X points and Y points, and it creates a matrix with every combination of those. So I'll show you a really simple example. So if I said X and Y are a mesh grid, are a mesh grid of the numbers 1, 2, and 3 for our x vector, and 4, 5, and 6 for our y vector. This is what pops out. Oh, x is equal to, not comma. Sorry. You probably caught that, and I did not. It'll pop out for your x. Every column is your x, and for your y, every row is your y. So if I wanted to create some third variable z, which is equal to x plus y, I'm able to come up with z being x plus y for every combination of x and y, right? Which makes sense. There are three x's, there are 3 y's. Therefore, your z is going to be a 3 by 3, or 9 of them, right? 3 times 3. All right. So what we could do is create a surface plot of x, y, and z, and show what x on one axis, y on another axis, with z being x plus y looks like. So I run that. Any day now. This is MATLAB's warming up this morning, just like us. There we go. Voila. We have x on one axis. It's going to be this axis on the right, y on this axis on the left, and then z. And of course, because this is a 3D plot, you can rotate it. Rotate it around and see how it moves. Pretty cool. We're going to do the same thing with our cost function, where on the axes, the x and y axes, we're going to have our 2 decision variables, and on our z axis, we're going to have our cost. So let's do that really fast with our cost function. So this is going to be our cost minus LH. We already have L. We already have H. So if we say that F is equal to, so we have to do a mesh grid. So we have to do a mesh grid here. We'll have to say, we'll call it L vector, or L, maybe L matrix, and H matrix are equal to mesh grid of L and H. I'm going to hit semicolon so that way it doesn't go crazy. Okay? Now, L and H should be big old, oh, you actually can see it right on the left here in the workspace, actually. You can see right there. It's a 1 by 100, 100 by 100. This is exactly what we want. Our HMAT and LMAT are 100 by 100 matrices. So we can then create our cost function. We'll say cost is equal to minus LMAT dot times HMAT, because we want every element of L to multiply by every element of H, semicolon, so we don't spit it all out. Okay. And now we can do a surface plot. I'm going to close the previous surface plot, close all. Yep. Testing 1, 2. Good. All right. And now we're going to do a surface plot of LMAT, HMAT, and our cost. Okay. And out pops this plot right here. I'm going to rotate it around. There we go. I should label some axes so we know what we're looking at. So let me label the axes real quick. I'm going to do X label is going to be our length. Y label is going to be our height. And Z label, that's how we label the Z. Z label is going to be our cost. Okay. There we go. I ran those 3 commands. And you can see I have my cost. And as you can see, if we want to have a very low cost, which direction do we want to go? We want to go down here, right? That's right. Okay? So, however, we don't have an unconstrained problem. We have constraints. Okay? So what I'm going to do is I'm going to try to plot what our constraints look like. Well, let's go back to our script. I want to now plot. So we plotted our cost. What do our constraints look like? What if we plot our constraints? Okay, why do we do that? Well, keep in mind we have some length and we have some height on this axis, and we know beforehand we can solve this out, okay, for this particular problem, that h is going to be equal to 20 minus L. That's just solving out the perimeter. That means that if we had 20 there and 20 there, it looks like that, right? For an equality constraint, this must. So the solution must be on that line. Okay? For an equality constraint, it's got to be there. So let's plot that line real quick. So let's go back to our curve. Okay. So we've got, so I want to be able to plot this line in this curve, which I can actually just keep this plot up and then plot another line on it by putting the hold on command on. And we can plot in 3D using plot 3. So what I'm going to do is I'm going to, since I know, I'm going to try to plot this this line right here with just 2 points. So I'm going to say that my H points are going to be at 20 and 0. My L points are going to be at 0 and 20. Basically, I'm going to plot the 2 points at the end of that line. Okay, this line right here. I'm going to plot this point, which is going to be 0, 20, 0, 20, and then this point here, which is going to be 20, 0. That's all I'm doing, just plotting this line, this point, and this point, connecting them by a line. The z coordinate, I'm just going to make it 0. Okay. So that means my z, sorry, my z points are going to be 0 and 0. Then I'm going to use command call, instead of plot, just plot 3. And plot 3 just lets you take an x, y, and z coordinates. It's amazing. So you could say, hey, I want my h points. Those are my horizontal points. My L points, those are my vertical points. And my z points, which are my, I guess, out of the board points. So x, y, and z. And I just want to make it a black line. I'm going to make the line width 2 so it's a little easier to see, friends. Line width 2. Okay, plot. Oh, I got to hold on before you hit enter. Got to hold on or else it'll blow away the plot. You can't see all that, so 1 second. Apologies. All right, hold on. Plot 3. There. I ran the code. Look at that. See that line? That's the line that the solution must exist on. Okay? So let's zoom in on that line, see if we can. Right now, the only thing I don't like, so maybe I'm too zoomed out. Let's change the axis limits. I can maybe just do this with the zoom command, but that can take a little bit of time. Let's zoom in here. Can I zoom in? That might be hard to do. Okay, what I'm going to do instead is I'm going to change the axis limits. So I'm going to say axis And you can change the axis limits by saying, hey, what's my minimum and maximum of my x coordinate? And I'm going to say 0 and 20. What's the minimum maximum of my y coordinate? I want to say 0 and 20. I want to zoom in a bit. Right now it's 0 and 40. And my z coordinate, I'm going to say 0. And with malice of forethought, we'll say minus 400. This is just me figuring it out. Did that not work? Oh, minus 400, 0. Technically, it's got to be minus 400, 0. The first number has to be less than the second number. This is the x coordinate, the x limits. These are the y limits. These are the z limits. Okay? Let's run that. I'm going to pull up the plot. Oh, look at that. Look at that. Not too bad. Okay, and I'm zooming here by trying to zoom. Let's see. Let's do the rotation thing. We'll just rotate this around. Let's take a look. So right now, you can see we have this constraint line and the cost function right here. You can see the cost function has a gradient. It has that curve. It's kind of curving down like that, right? Okay. Now, geometrically speaking, we're going to want to come up with the minimum cost, in a sense, by finding where the gradient gets down, 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 and then levels out at 0. Okay? The problem is that with a constrained optimization, we actually know where the best solution is. It's going to be at minus 10, 10. Where is it? Right here? Right there. In fact, we could plot that point right there. Let's do that. Okay. I'm going to say hold on. I'm going to plot in 3 dimensions. I know where the best solution is. We know it's all at 10, 10. We'll say 0. And we'll make it a black circle so you can see. 10, 10, 0. A little black circle there. It's a little small. So let's go make it a little larger. We'll say marker size 20. It's a little bigger. It's still hard to see. It's still too thin. Okay? But it's right there. I'm not sure you can see it that well. Okay? What you're going to find is that if you look at the gradient of the cost function as it butts up against that line, it's going to be pushing directly into that line. Okay? It's not going to be pushing to the side. It's not going to be scooting off in that direction. It's going to be pushing at that point directly into that line. Okay? What do I mean? So maybe there's a different way to show this. I'm going to create a new plot. Instead of plotting a surface where you actually see the height of the surface, we're going to plot a contour plot. Okay? I'll show you what I mean by a contour plot. Contour. Same inputs as our surface with our x points, which are going to be L mat, our y points, which are H mat, and our z points, which are going to be cost. Here we go. Might be a little hard to see because of the colors here. Maybe change the line width a bit. Perfect. Perfect. I changed the line width to 3, if you can see that. All right. This is our cost contour. See that purple up there? If you're color inclined, that's a high cost. As the color gets closer to red on the rainbow, the lower the cost. So you can see these. It's like a topographical map of the cost. Sometimes we'll call it the cost landscape, right? If you were following which way to move where the cost goes down, you'd go down this way, right? That's the way the cost is most decreasing. Most decreasing, that in that direction. I'm going to put the constraint line on this, so I'm going to say hold on. I'm going to plot on this. I'm going to say 0, 20, and then 20, 0. I'm going to put a black line with a line width of 3. Oh, here we go. I had it reversed. I'm sorry. Purple was actually lower cost. That's good. Red on the spectrum is high cost, which is bad. And there's our constraint line. See that? So if we want to follow which way we want to reduce the cost, we want to go in that direction. Well, we bump up into this hard line right here, right? And so what I want to show you is that the direction of the gradient at the optimal solution is going to be pushing directly into that line. Directly. Okay. What does that mean? Let's go into our whiteboard. At the optimal solution, for a constrained optimization problem, the cost gradient will be pointing perpendicularly to the constraint line. So if we have, in this case, a length and a height, and here is our constraint, and if we're going to point to where the gradient of the cost is pointing, at the optimal solution, that's W star, this here is going to be the gradient of our cost. Okay? Because you think about it, at the optimal solution, if it weren't perpendicular to that constraint line, let's just say it was pointing off a little bit askew, then it would see an incentive, it's a little askew over there, it would see an incentive to lower cost by sliding over here on the constraint line and kind of slip off, like my hand's going shook, like if I'm doing this with my hand. If I'm pointing straight in and I'm pushing, there's a pressure to decrease cost in that direction. It won't go anywhere. But if there's a pressure a little off to the side, shook, it'll slide off and keep going, right? So that's a mathematical condition that we can take advantage of for a constrained optimization. I appreciate you following me on that. I'm happy to take questions on it. But that's what's going to motivate this idea that for a constrained optimization with equality constraints, we can use that gradient information of the cost and how it relates to the constraint to come up with a new first order necessary condition for constraints. Okay? So that means that we can have a new first order necessary condition. optimizations. We have a new first order necessary condition, okay, where we create a new condition where instead of partial f of w equals 0, we create a partial L of w equals 0. And I'll make L a fancy L, so it's not like fancy L. It has to be a fancy L. Otherwise, there'll be length in the problem we just did. It's got to be fancy L, okay? Where L is equal to our cost function, that's the same, plus this term here called lambda transpose times g of w partial w equals 0, where L, as you can see from this relation, is our cost function plus this lambda times our constraint. Okay? And this is called the Lagrangian. Okay? Called our Lagrangian. And lambda, they are called Lagrange multipliers. You could think of them as a constraint force. Okay? So here's the idea. All right? So we've got this constraint line that it's got to exist on or not go past if it's an inequality constraint. You have to exist on if it's an equality constraint. My pressure from my cost is going to have a gradient pushing in some direction, right? I want to go there. I want to go there. I want to go there. The Lagrange multiplier you can think of as a constraint force. It's the thing that's pushing back. It's pushing back to hold it in place, okay? And that's what lambda is, right? So if you were just minimizing this cost here, okay, it would try to send that gradient to 0, nothing stopping it. However, if something is stopping it, it's going to be some metaphorical force that acts along the constraint, okay? And when you take the derivative of it, as you do up here, this enforces the condition that it must be that constraint force must be acting in a direction perpendicular to the constraint line, okay? So you'll see you'll be taking the derivative of our constraint with respect to w, which is what? Our gradient, okay? So what numbers can our constraint force be? Well, they can be all kinds of numbers. They are scalar values. They are real numbers. We'll say m, whereas w are real numbers. There are n of them, where you have n decision variables. And m equality constraints. Okay? And they could be any number. However, when you add these constraints, these Lagrange multipliers, it's not enough that the derivative of your Lagrangian is equal to 0 with respect to your decision variables. Also, the derivative of your Lagrangian with respect to your Lagrange multipliers must be equal to 0. So you actually have two conditions here. I'm going to write them both next to each other. Partial L, partial W is equal to 0. And partial L, partial lambda must be equal to 0. Those are your new first order necessaries. Both have to be true to solve the problem. Okay? So we have these new first order necessaries. So what that means is we could use this to try to solve our optimization problem, our constraint optimization problem. Let's try using gradient descent, like we talked about last time. Let's see if we can use gradient descent to try to solve this problem. Now knowing that we need to have a Lagrangian and find the point where the derivative of w and the derivative of lambda, with respect to lambda, are equal to 0. So let's try this out in code. Okay? See how this works. So I'm going to create a new script. I'm going to call it fencing Lagrangian.m. I'm going to save it as that. I'm just going to save it as fencing Lagrangian.m. All right. By who? By me and my two friends here. Thanks for being here. All right, we got 2025, 02, 04 of the Common Era. We're going to solve a constrained optimization problem via gradient descent on the Lagrangian. Okay? And here's a fun fact, folks. This constraint force, this Lagrangian, okay, that acts in a certain direction, I'm talking about as a metaphorical constraint force in this problem, right? It's pushing you in a certain direction. Later in the class, when we talk about modeling mechanical systems with physical constraints like joints and connections, that Lagrange multiplier shows up again. And it's not just a metaphorical force, it's a physical force. So it actually has a real physical meaning when applied to physical systems with physical energy, okay? So stay tuned for that, all right? All right, back to coding. We're going to clear everything. Okay, we're going to clear the screen. We're going to clear all the variables. We're going to close all the plots. Okay, now, I want to solve the fencing problem, which means I need to come up with a Lagrangian for my fencing problem. We'll go back to the big screen for just a second so you can see a little easier. So the Lagrangian is going to be a function of all of our decision variables and our Lagrange multipliers. Again, these are just scalar values. They're real numbers, these Lagrange multipliers, okay? And that's going to be equal to f of w plus lambda g of w. Well, let's remind ourselves that our w is going to have our length and our height. Our f of w, that's going to be our minus L times w. Our g of w is equal to 20. What do we say? 2L plus 2W. I did it again. Lambda transpose. Thank you. Lambda transpose. Got ahead of myself. Lambda transpose. Thank you, Angela. And I also almost forgot that it was H instead of W. Minus 40. Okay? We got that. Lambda transpose. Thank you. In this case, it won't matter because the lambda transpose, that's not an excuse. It's just letting you know. Because how many lambdas do we have? We only have one equality constraint. Therefore, we only have one lambda. And it's a real number, r. Okay? So what we need to find is a L, an H, and a lambda such that partial Lagrangian of W lambda partial W equals 0. This is our first order necessary conditions. And of course that partial W partial L of W lambda partial lambda is equal to 0. We can try to solve that via gradient descent, right? That's what we're doing. Okay, so back to our Lagrangian of W and lambda is going to be our cost function way up there plus lambda transpose. There's only one lambda, so it's not even a vector. It's just a scalar number times GW. So that means we're going to have minus L times H plus lambda. Again, there's the only reason it's not a transpose is because there's only one lambda. We only have one of them. Okay? Times 2L plus 2H minus 40. Okay? That's our Lagrangian. Okay? And if we're going to want to do gradient descent, let's figure out right now what those gradients are. We could use the symbolic toolbox. We could also do that, but you know, let's keep it simple for today. Okay? So, what's our partial Lagrangian partial W? Well, that's going to be a gradient. Okay? Where this is going to be partial lambda partial length. Then you have your partial lambda partial height as your second entry. Okay? So partial L partial Lagrangian partial L, it's going to be minus H, so that's a constant, minus H, plus, here's an L. Oh, that's going to be a constant. That's going to be a constant. It's going to be multiplied by lambda. So it's going to be 2 times lambda. So plus 2 lambda. Then you're going to have partial L, partial height. Partial L, partial height is going to be very similar. It's going to be the coefficient in front of H right there, so minus L. I'll zoom out a touch. Then you're going to have, where's your H's? There's an H there, so that's positive 2 lambda. That's going to be a constant. That goes away. So it's going to be plus 2 lambda. Okay? All right. That's cool. But we also need to know partial L, partial Lagrange multiplier. Well, what is that? Let me write it down here. Partial L, partial Lagrange multiplier, lambda. Well, the only lambda that I see is up there. Right next to lambda is this. That's a whole constant, right? That's a constant. That'll go away. So it's just going to leave 2L plus 2H minus 40. And for the first order necessary conditions, all these things we want to equal to 0, right? So here's what I'm going to do. I'm going to try to treat these all as one vector. And apologies if this screws up your notes ever so slightly. Of variables whose gradient I want to descend here. Okay. So I'm going to try to do gradient descent. I want all these things to equal 0? Interesting. Interesting indeed. Okay. Let's go back to our code. So we're going to do a gradient descent I'm going to create a function. I'm going to say partial L probably too many L's and Lagrangians here, okay? Here's what we're going to do. Okay, we're going to start with just simple unconstrained gradient descent. Okay. We needed to define a step size. Let me just remind everyone the formula here. That we had WK plus 1 is equal to WK minus partial F of W partial W times alpha. Okay. That was our formula. So we need what? We needed a current. We need a current guess. We'll call that WK. And we need a guess for our length. Let's guess our length of 6. Let's guess our length of our width, our height of 6. And we're going to make our step size. Let's make our step size, call it alpha. It's equal to, I don't know, 0.5. Okay. Then we need wanted a threshold, you'll recall. This is how we know if we stopped, if there's a value is less than a certain amount. So we'll call it a threshold is equal to 1e negative 2. So that's 0.01. This is stop if the gradient is less than this. Okay. Okay. Now we're going to do a gradient descent loop. Give us a little bit more space. Not too much. We're going to create we'll do a for loop to start, just because in case things become an infinite loop, we will definitely stop. So we'll say we'll do 10 iterations. So a for loop with 10 iterations. So iter is equal to 1:10. All right. We're going to say, hey, what is our gradient? Or our gradient here is minus h. Let's create a function for our gradient. We'll call it my gradient. What does it do? It takes in W, and then it's going to spit out our gradient of partial L, partial Lagrangian, partial L, partial Lagrangian partial h. So it takes in W and spits out minus h. We'll just give it HL and lambda. Sorry, stop for a second here. Minus h plus 2 times lambda. What? I need to know what lambda is to know what my gradient is, right? So that means my gradient needs to know what lambda is. And lambda is going to be solved for just like anything else. Okay? We are trying to define what our decision variables are, our length and our height. But we also need to figure out what lambda is, which means that our thing that we're optimizing, our decision variable space, also includes lambda. And we already kind of laid this out for you. Look at this. Here, you have your Lagrangian with respect to L, your Lagrangian with respect to H, which are your decision variables, but also Lagrangian with respect to lambda. Okay? And all of these three gradients have to be equal to 0. So let's treat lambda, our Lagrange multiplier, as if it's a decision. And if it's a decision, then just like everything else, we need to have an initial guess. We have an initial guess for length. We have an initial guess for height. Let's have an initial guess for our Lagrange multiplier. I don't know, 1. We'll see what happens, okay? So our gradient is minus h plus 2 times lambda. And our second element of the gradient is minus L plus 2 times lambda. And our final one is, we'll put on the next line with an ellipsis here, is going to be 2 times L plus 2 times H minus 40. Okay? So that's going to be your gradient. This is your gradient function. And it takes in your current H, your current L, and current lambda, and returns d Lagrange, dl d length dl d height and dl d lambda. I'll put this on the next line a little bit. Scoosh that back in so you see all of it. There we go. There we go. Okay, got a gradient. So we have a gradient. So that means that WK, the next one, is equal to the previous WK minus alpha times your gradient, which you can get by saying my gradient, and giving it the current height, which is going to be W1, our current length, which is going to be W2, and our Lagrange multiplier, which we're pretending is our third decision. So W3. Okay? And then we're going to run this for 10 iterations and see what happens. Okay? Let's go. Oh, it didn't like W. Oh, WK. This says just say WK right here instead of W. WK, WK, WK. Running. Lambda. Oh, LAMB. Lambda? I'm blanking. Is there a B in lambda? There is today. Okay, things seem to be going crazy a little bit. Let's try a different alpha. Okay. I think I screwed something up with the math here. Alpha WK. What's WK? I think I screwed something up in the math. Just do a quick little debugging. We're almost done. I think I screwed something up in the math. Alpha should be a constant. Because what's happening, what I'm noticing here, friends, is that WK becomes a matrix. It totally shouldn't become a matrix. So what happened here? We've got 0.05, 2h plus 2 lambda. Let me stop it after. Here's a good debugging trick. Let's do it only after like 2 iterations and see what happens. Because looking at this, after the first iteration, WK becomes a matrix, and it totally shouldn't be a matrix. My gradient here, it should not be semicolon. That should be comma. Comma. That's one thing that I need to fix. That should be comma. There we go. Comma. Now I think it's going to work better. Okay. All right. I'm going to change it to 10 iterations. Okay. And it's creeping up, creeping up. Minus 40. 100. Yeah, I think I screwed something up again. I'm going to have to fix this after the lecture here. We're almost out of time. But I'm trying to do a gradient descent loop where it tries to do a gradient descent not only on the decision variables, but also the Lagrange multipliers. Okay? So, with that, we're going to finish up a little bit later, probably finish this up at the beginning of the next lecture. But the core idea is that when you add constraints, you can add Lagrange multipliers to help you solve for those constraints, as opposed to just solving for them in terms of decision variables and resubstituting them. All right? That's the core idea. All right, Angela, you have a question? Yeah, it should. It should. It absolutely is a great question every time, because it's now updated WK. Therefore, your gradient will update every time, right? So let me try a different initial guess. Maybe that might solve the problem. No, it didn't quite solve the problem. In theory, you can include the threshold to have it stop, but you'll notice that even without the threshold, it goes to crazy numbers. So clearly, it's not ready to stop, right? Because right now it's saying it's going to a million, which ain't right. So something got screwed up here. Okay? So, but I'll fix that offline. I'm not sure I'll be able to debug this in the next couple minutes, though. But yeah, so when you're done, Angela, so you could turn this into a while loop and say, while the threshold is not met, keep going. But here it would have an infinite loop. That's why I didn't do it. You got it. All right. Thank you all very much. You all have a good day. Look forward to fixing this up. Good luck. You too.